Hi class, this is another uh, practice video. This is not really intended to be a lecture. It's supposed to be done after you've completed the relevant 2.3 and 2.4 sections, or at least familiarized yourself with the material. But I will kind of review some big picture stuff as we get started. So we're talking about truth tables for arguments in the indirect method. So suppose you have an argument, premise, if A, then B, premise, not B, conclusion, not A. So I always like to put a double line there to remind me it's the conclusion rather than another premise. We can determine the validity, that is, we can determine if this is a good argument using truth tables. Why? Remember, a truth table is a presentation of all possibilities, and we could define validity in terms of possibility. A valid argument is one in which it is impossible for all premises to be true and the conclusion false. So what do? Well, first you do a truth table. How many individual constants do I have? 1, 2, so my n is 2, 4-line truth table. So I'll go by 2's for all instances of A, and I will go by 1's, having it for all instances of B. Hopefully you don't have too much difficulty doing that. Oh, sorry, autofocus. And after that, you compute the truth value as always. Well, if true, then true is true. False, true, true. There's the all possibilities for the first premise. Negation simply flips the sign. There's all possibilities for premise 2. Negation once more just flips the sign. There we have what is circled is all possible values for both premises and the conclusion. But how do we use that for validity? Reminder, a valid argument is one in which it is impossible for all premises to be true and the conclusion false. So, is it possible means, is there a line with all true premises and a false conclusion? Well, let's check. True premise, false premise. False premise, true premise. True premise, false premise. So I don't even have to worry about those because clearly they can't have all true premises. Oh, wait a minute, all true premises, but a true conclusion. So there is no line on which all premises are true and the conclusion is false, which means it's not a possibility. And so we call this argument valid. I don't know why my autocorrect is being so bad today. I apologize. That's the truth table method of determining validity. However, 2.3 and 2.4 present two further concepts of validity. The one is called the indirect method or assigning values. How does that work? Assume I had the same argument, if A then B, not B, not A. If we're looking at an argument and I want to know whether there's a line where all premises are true and the conclusion is false, the other thing I could do is just kind of work backwards to see what that line would look like, i.e., see if that line was possible. And that's what we mean by the assigning method, or sometimes called the indirect method of truth tables. So what I'm really after is there a line where this premise is true, that is a T under a horseshoe. This premise is true, that is a T under the negation. And the conclusion is false, that is an F under the negation. Well, to do the indirect method, I basically am asking, is this line on the truth table? And how do we go about figuring that out? I like to use what I call the Halfto method. What would that line have to look like? Well, I just started the first premise. How many ways could a horseshoe be true? 3. And so nothing has to be the case there. A and B could both be true, A and B could both be false, or A could be false and B could be true. So I don't mark anything, I move on. How many ways can a negation be true? Just 1. The only way a negation could be true, if we go to the negation line in the truth table, is if what it's negating is false. It would have to be line 2. So if this line appeared on the truth table, it would have to be one of the lines where B is false. So I'm going to go back and fill that up. However, it would there's also only one way not A could be false, and that's if A is true. And so I go in and fill in A is true. Then I simply ask, is this line on the truth table? Does this line appear on the truth table? If so, the argument is invalid. Would it? That's a way of asking, is this possible? And if you pay attention, the answer is no, because in order for this line to be possible, we would have to break a law of logic. We would have to basically change the rules of horseshoe so that if true then false, registered as true. And so in order for this line to be on the truth table, we would have to do a no-no, which tells me that no, this line cannot occur on the truth table, which is a second way to render it valid. There is a third way of determining validity that is introduced in 2.3. It's introduced relatively quickly, and that's called the corresponding conditional. Why? Because if you recall, a corresponding conditional, if you recall, a valid argument, one way of defining validity, as we did on the first video, is is an argument whose premises imply their conclusion. But wait a minute, we know how to formalize imply. A valid argument is just one that says, if the premises, then the conclusion. If the premises, if premise 1 and premise 2, then the conclusion. So do this in 2 steps. First of all, this is the corresponding conditional. This conditional corresponds to this argument. It says, if all premises, then the conclusion. And in a valid argument, the corresponding conditional is a tautology. So we just have to work out the truth table. It's going to be a 4-liner. Sorry if I do this a little fast, but hopefully you should be in a position to do it relatively quickly yourself now. Negation of it. Oops. That would have screwed me up nicely. Negation of atomic. False, false, true, true. And then we have false, true, false, true. Then we have true, false, true, true. Now, here, notice that one of the ways I did that so fast is because up to now, everything is the same as premise 1. And so now when we do this conjunction, that's a conjunction of the premises, we're doing when are both premises true? False, 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 true. Notice this corresponded to line 4 up here was the only line in which all premises were true. And then we do the corresponding conditional, says if the conjunction of all premises, then the conclusion. If false, then false is true. If false, then false is true. If false, then true is true. If true, then true is true. So when the corresponding conditional is a tautology, the argument is valid. So those are three ways you can test for validity using truth tables. Again, hopefully this is just practice. The one thing I will say, the exercises ask you to extend what you know about the indirect or assigning method a little bit to determine whether a statement is a tautology. You should be able to figure out how to do that, but remember, a tautology is when it is impossible that it is false. And so if you want to test using the assigning method, you just assign it's false and see if you can find a contradiction. And if you want to extend your thinking a little further, then you can also test whether a statement is contradictory using the indirect method, or also known as the assigning method. And you could also use the method of assigning for determining whether statements are consistent. So anyway, more on that in the recitation, but you are responsible for all three of these methods on the exam. Having said that, the purpose of this video is not so much a lecture as some practice. So let's do a couple of the trickier problems using these three methods. And again, I'm doing ones that are out of the book that hopefully you have already given the old college try, so to speak. But let's go ahead and sorry, I'm deciding if I want to do one in the book, but there's really not that many in the book, so maybe it's best if I just do another one. Here's an argument. L if and only if, not M, premise. If M, then C, premise. Not C, therefore L. There's an argument. So if I want to do the direct method of truth tables, what do? I make a truth table. It's going to be, let's see, L's and M's and C's. It's going to be 8 lines. And I do my truth tables accordingly. However, suppose I instead wish to do the indirect method, also known as the method of assigning values. Well, what would that require? Instead of completing a truth table and just looking for a line where all premises are true and the conclusion is false, I instead ask, what would that look like? Well, it would have to be a T here, a T here, a T here, and an F here. And now I simply ask, is this line on the truth table? Let's see. Again, I start with what would have to be the case on this line. And so I start by asking myself, how many ways can triple bar be true? 2, if they're both true or they're both false. So nothing has to be the case there. How many ways can horseshoe be true? 3, so nothing has to be the case there. Wait a minute. How many ways can a negation be true? Just 1, if what they're negating is false. And sometimes if I finish a premise, I like to put a check mark over it. Similarly, this one's done. So this would have to be one of the 8 lines of the truth table in which C was false. And so that would have to be here. Okay, here's a move you need to get familiar with, just with practice. So let's go back to the if P then Q truth table. TTFF, TF, TF. All right. Which line am I at on the horseshoe truth table? Again, this is a move you're going to have to make a lot. Well, it's one of the lines where my Q is false. So I'm not on line 1, and I'm not on line 3. However, I know one more piece of information, that the horseshoe is true, which means it also cannot be line 2. So if the whole horseshoe is true and C is false, I have to be on line 4. It has to be if false, then false, which means M would have to be false, which means this is true. And let's go to the triple bar, P if and only if Q, P, T, F, F, T, F, T, F, true, false, false, true. What do I know about this setup right here? Well, I know it has to be one of the 2 lines in which triple bar is true, so it's not line 2, it's not line 3. But wait, I also know that my Q is true, so it's not line 4, and so L has to be true. Does this line occur on the truth table? Careful, because we computed all the premises, but we never looked at the conclusion. So if I'm asking whether the line's on the truth table, I'll usually do 2 things. First of all, I'll run it all through forwards, and then I'll double check the letters. So let's run it through forwards. What does that mean? I'll just look at this. Well, not false is true. If true, then true is true. If false, then false is true. Not false is true. That's what I mean by running it forwards. But then I will check for consistency. L is true here. Ooh, L is false there. What does that tell you? The only way that this argument could be valid is if we broke a law of logic. In order for this argument, to be invalid, in order for us to have all true premises and a false conclusion, L would have to be simultaneously true and false. That is an impossibility. That is an abomination of logic. It is not possible for L to be both true and false at the same time. Hence, we know that this line cannot occur on the truth table, which means we know this argument is valid. And again, write your answers. Don't do all the work and then not apply it. All right. Let's do a few more with the method of assigning values. So here's an argument. If S, then M. If M, then T. If T, then S. Therefore, M or S. So, what's our method? If we're doing the direct method, we do, again, an 8-line truth table and look for one line in which every premise is false and the conclusion is true. If we are doing the corresponding conditional, we turn it to a conditional. By the way, as a quick little aside, say you have premise A, B, C, and conclusion D. For reasons we will talk about next unit, you could conjoin all premises like this, or you could conjoin all premises like this. It doesn't actually matter. Oops. Because Oh, shoot, I'm doing the wrong conjunction again. These two are equivalent. By the law of commutativity, you could do that with conjunctions. If you don't believe me, you have the tools to prove it. You could actually do a 16-line truth table to prove that this is equivalent to this, and you are absolutely welcome to do so. But anyway, so if you have three premises and you're worried about how to conjoin them, it doesn't matter since it's just conjunctions. But suppose we're not doing the corresponding conditional. Suppose we want to do the assigning method. Again, I want to know, does this line occur on the truth table? One in which there's a T under each main operator and an F under the conclusion. And I'll ask, what does this line occur on the truth table? I then ask, what would it have to look like? Well, how many ways can a horseshoe be true? 3. How many ways can a horseshoe be true? 3. How many ways can a horseshoe be true? 3. How many ways can a disjunction be false? 1. The only way in which a disjunction can be false is if both of the disjuncts are false, which means if this occurs on the truth table, I've just narrowed the possibilities quite a bit, because it would have to be a line in which both M and S are false. So I'm going to go back. S would have to be false for all instances of S. M would have to be false for all instances of M. Okay, so that's taken care of, and if false then false is true, that's taken care of. Well, do we know anything about T yet? Nope, because how many ways can if false then blank be true? 2. We could be on line 2, we could be on line 3 or line 4 of the horseshoe truth table. So I move on. This is the same inference as before. I know the whole inference is true, so I'm not on line 2, but I know that the consequent is false, so I'm not on lines 1, not on line 3. So, once more, this would have to be false. The only way to get, if T was true, it wouldn't work. And so, false. Okay. So, this seems like what it would have to be in order for this line to occur on the truth table. It would have to be a line, well, let's double check to make sure that this is possible. If false, then false is true. If false, then false is true. If false, then false is true. If false, then false, false or false is false. Then we check for consistency. S is false here, here, and here. M is false here and here. And here. T is false here and here. Yep, that seems to be possible. We have not broken any law of logic to do this, which means this line does occur on the truth table, which means it is invalid. For kicks, which line of the truth table would this be? The line where all 3 are false is line 8. So, a good exercise, if you need a little practice, do the direct method of truth table for this, and you will see that on line 8, all premises are true, and the conclusion is false. So that is an invalid argument. If you want to really kick it back to some of those optional introductory lectures, you could probably also find a counterexample to this pretty easily. If Mickey is over 12 feet tall, then he is over 10 feet tall. If he's over 10 feet tall, he's over 8 feet tall, et cetera, et cetera. So there we have some good practice on the indirect method. But again, these videos are not a replacement for you doing the work yourself. You have to practice, practice, practice. This is a timed exam, so make sure you're doing it enough to be comfortable with it. We will talk more about the exam format and expectations on the review recitation. And so make sure you're bringing your questions. In fact, be sure you're writing down your questions before we come to that as well. And we will see you next time.